Okay, so then we have derived the expression for g of ne in three different situations, and now we will specifically take the case of Maxwell Boltzmann. So we substitute that over there in equation number 4. We substitute equation 5 in equation 4, right? So while substituting that, we will get Q1 Vt is equal to sum over and Ne product over 1 by Ne factorial e raised to minus beta sum over Ne, right? So I can, instead of this summation in the exponential, I can always express this part of the equation as products, right? Product of the exponential values. So sum over Ne factorial 1 by Ne factorial into product over e raised to minus beta Ne e. Right, simple. Instead of the summation in the exponential, I have put so this is what it physically, the mathematically means by. Now what I do is that multiply by n factorial in the multiply and divide by n factorial in the above equation. Then I will get Qn Vt is equal to 1 by n factorial product over Ne n factorial divided by product over e Ne factorial into product over e raised to minus beta Ne, right? So this equation above, now let me put this equation 8. So the equation 8 can be simplified using multinomial distribution. What is this multinomial distribution means by? Multinomial distribution means that if I have a set of values a1 plus a2 plus up to ak, that means I have k number of terms. So number of terms is k, and I am exponentiating that and having the power value of n, then I can write this value can be expanded as equal to sum over n factorial by n1 factorial into n2 factorial up to nk factorial product over akn. So this is how you expand it, where n1 plus n2 plus up to nk is equal to n. So this is the definition of multinomial distribution or the multinomial expansion. So these are the values. I have k number of terms raised to the power n. When I am expanding that, I can expand it as sum over n factorial by n1 factorial into n2 factorial into n gap up to n gap factorial. Product over, this is product, product over ak raised to n. So this is how I define that. I can substitute this over here, right? Here, right, I can write it as QNVT is equal to 1 by n factorial, this n factorial, right? So I am going to expand this, and I am going to apply this into here. So n1 plus n2 plus nk is equal to n factorial. So therefore I can write it as summation over e raised to minus beta e raised to n. Because my n, capital N is n1 plus n2 and n1 plus n2 plus n3 plus n. So my small n over here is actually my capital N over here. So that's why sum over e raised to minus beta e raised to n. Right, therefore I can write this as 1 by n factorial into q1 vt raised to n, right? So Q1 Vt is equal to what? Q1 Vt is equal to sum over E, because I know that the Q1 Vt is equal to Q1 by n Q1 raised to n by n factorial. So my Q1 is now sum over E raised to minus beta E, and that I can write it as, therefore Q1 is equal to Q1 Vt is equal to sum over E raised to minus beta e. Now this integral, sorry, this summation can now be expressed in terms of the, can be approximated in terms of the integral. The integral by assuming that I am considering something like the density of states. Why? Because it's again in this case also I can always assume that the volume is huge compared to the total volume of the number of particles in that, and therefore I can move myself into the regime of density of states. So with that concept I can move from the summation to the concept of integral. So what is the kind of change I should be making there? So while I am moving from this discrete states to the density of state case, I have already discussed that in the case of, I think it was discussed in while we were discussing about the classical particles, right? So it goes something like this. So now what we are trying to find out is that what is the kind of conversion factor. We have already done those kind of things in the past when we are dealing with the classical mechanical particles. So let me repeat that over here. The only difference is that we have to express it now in terms of the energy, because we have the energy over here. So we are now in the QP regime, right? So this is the sphere in which all the ideal gas particles are located. And we know that so if we have to calculate the density of state, what you have to do? The density of state can be approximated in terms of the in terms of the concept that we have what is the total volume divided by total by the volume of each of the particle, each of the constituents, right? So the total volume, how do we do that? The total volume. So I have the QP space. The total volume in the Q space is given by capital V, X, Y, Z, right? And in the P space, I can write 4 by 3 pi P cube, right? And when I'm converting myself, so in this kind of picture, the volume of 1 microstate is h cube, because that is the kind of we have discussed that already in the past. H is the kind of uncertainty in one dimension, and then therefore the h cube as the volume of one of the microstate, right? So I can always write the density of states in terms of the momentum space as AP dP is equal to d by dP of V by h cube 4 by 3 pi P cube. Right, if I am trying to write in the energy sphere, in terms of the energy, I have to just substitute P squared by 2m is equal to E. So if I express this same expression in terms of the energy, I can write it as d by dE of V by h cube 4 by 3 pi two E raised to 2m E raised to, right? Raised to cube 4 by 3 pi P cube 4 by 3 pi P cube. P is 2m into root of E, right? P squared by 2m is equal to E. So therefore sorry, I did the mistake. AD is equal to d by d of V by h cube into 4 by 3 pi root of 2me raised to cube. So that's it. So I can simplify this and put the differentiation and all that, and I can write as V by h cube into 2 pi into 2m raised to 3 by 2 e raised to half d. So this is how I will express the and therefore while converting from summation over e raised to minus beta e can be converted into integral using this kind of a conversion factor. So which is V by, I have to just multiply it by AED, right? So integral V by h cube 2 pi into 2m raised to 3 by 2 e raised to half d e raised to minus beta e. So this is how I convert it. So I can always put the appropriate things outside the integral, and ultimately I can write q1 Vt as roughly equal to 2 pi v by h cube into 2m raised to 3 by 2 integral 0 to infinity e raised to minus beta e raised to half dE. So this is the new form of Q1 Vt when I am expressing it in terms of the integral. Now let me put myself into the K sphere. So actually I should not have written that. So this should be written in the blue. So and there I was trying to tell you how this value okay. So that is a new expression for Q1 Vt, and now you substitute E is equal to h squared k squared by 2m into this expression, and then I will get Q1 Vt nearly equal to V by 2 pi cube 4 pi into integral 0 to infinity dk k squared e raised to minus beta h squared k squared by 2m. Okay, by 2m, and that can be written as equal to v by 2 pi squared into half into gamma of 3 by 2 2m by h squared beta raised to 3 by 2. Why? Because you have to always see the definition of gamma functions. Gamma of t is equal to integral 0 to infinity x raised to t minus 1 e raised to minus x, right? E raised to minus x dx. So therefore gamma of 3 by 2 is equal to and also so here for making this kind of conversion I will assume my x is equal to some constant into k squared. This is my x now. So this is the basic expression for any gamma function, and if in this expression if I take x is equal to some constant, the constant is of course but my beta is squared by 2m, right? So constant into ck squared. So that is how I do that, and this I can express it as equal to v by v into m by 2 pi beta h squared raised to 3 by 2, because gamma of 3 by 2 is equal to 1 by 2 into gamma of 1 by 2, which is equal to root pi by 2. So while applying all those things we get this expression. So this is the expression for Q1 Vt, and we know the expression for lambda, right? The de Broglie wavelength, and I have in the previous video, in one of the previous videos I have return a different kind of expression for the lambda. Lambda is h by 2 pi m k t raised to half, but we can always express it in terms of the beta also, right? So based on that, I can write this as v by lambda cube. So q1 vt, therefore q1 vt is equal to v by lambda cube, and q1 vt is equal to v raised to n by n factorial lambda raised to 3n. Because why? Because in an ideal, the q1 vt's general expression is q1 raised to n. But when it comes to ideal gas, we have to, in the classical regime, and in those cases in which the particles are distinguishable, where we have made a general assumption that it has to be divided by n factorial. So this is the same expression which we got in the case of classical particles. So this is the expression for Maxwell Boltzmann statistics in canonical ensemble, right? Because we have started with e raised to minus beta e, which is corresponding to the canonical ensemble cases, and here we are talking about we applied the g of mb, right? The weight factor was applied for the Maxwell Boltzmann statistics. So this is the Maxwell Boltzmann partition function for an ideal gas, which we found out that this is equivalent or the same as the expression we found out for classical ideal gas. You can go back to your notes and see for yourself. So whether we derived in terms of quantum mechanical or in the classical, in the case of Maxwell Boltzmann, they are one and the same thing, which means that we were actually talking about that is why we talk about that Maxwell Boltzmann is actually corresponding to the classical treatment of the ideal gas. And yeah, that's it. So the rest of the things for the grand canonical ensemble, and that for the Bose-Einstein and the Fermi-Dirac case, we will discuss in some other videos. Okay, thank you.